Morning and good afternoon, everyone. I hope you can hear me. My name is Britta Isaacson, and I am the Global Segment Manager for Food and Beverage in ABB's business area Motion. I have the pleasure to welcome you today to this food and beverage webinar on cooling towers, a solution for lowering energy consumption and reducing noise and total cost of ownership. And for this webinar, we invited Michael Klein, who is our area sales manager in Europe for business line, motors and generators to hold this webinar. Michael is based in Germany and has more than 30 years of experience working in ABB, of which 26 years are in the field of NEMA motors. So in this webinar, Michael Klein will describe a solution that lowers heavy maintenance costs at the same time as it saves energy. Enhances safety and lower noise from cooling towers based on a unique motor drive combination. This webinar will take 60 minutes, of which 45 minutes will be presentation, and then we will open up for a 10 to 15 minutes Q&A session at the end. During the webinar, your microphones will be muted, and please note also that this webinar will be recorded. So if you have any questions, I ask you to please tap them into your either chat window that's on the top of the panel on the right-hand side or in the Q&A window. And if you are using the Q&A window, make sure you use the drop-down menu to address questions and make sure that I as host see this so I can read it at the end. But with this, now I would like to hand over to our presenter of today, Michael. Please go ahead. Thank you.
Thank you very much, Britt. Hopefully everybody can hear me. Good morning, good afternoon from my side as well. And yeah, we want to talk about cooling tower motors today. Britt had said already everything positive about this product. Let's see what I can add to this. The agenda, real quick, is the cooling tower application. So in case there is someone on the phone here that doesn't know what a cooling tower is, I want to explain it a little bit. Then our innovative motor technology to improve the complete cooling tower performance. Then I want to tell you that it is a proven motor design. It's a very proven design already since out on the market since many years. Then we have some measurements from the field installations, and that is really nice because we have one measurement from the US and one measurement from Denmark, and so two total different countries, and the results are very similar, if not the same. And then we come to the summary and then the questions, of course. So this is a plant, a food and beverage plant. I must admit, this is in the States. And first of all, from that Google view, you see a plant, but you don't spot really the cooling towers. But you can spot the cooling towers. Look at this. These are all cooling towers. There are 46 cooling towers in that plant. So you see the red circles, and there you see various sizes of cooling towers. They're exposed, of course, to the outside. So Google View is a very good tool to see where cooling towers are installed and operated. We have three different main types of cooling towers. The wet cooling tower, that's the one we want to talk about today. That is the innovative product that we have designed especially for this wet cooling tower. The ACC, the air-cooled condensers, we have a product for that as well, but we are not touching this today. It would be a separate webinar. And then the air-cooled heat exchangers. These things are smaller fans with multiple fans. So it's a complete bank of fans. We have products for this as well, but we're not touching on that. It would be then 3 webinars in total. So we touch on the wet cooling tower, and there are over 17,000 towers in operation with an average of 3,000 retrofits per year only in the US. The whole world has far more than this. So it's a big market. There are cooling tower OEMs out there that are producing new ones and do refurbishments or retrofits on these. We can basically go into the new business as well as in the new installations as well as in the retrofits. Our product is not limited to either or. Here the air-cooled condensers, these are these huge, massive monsters. There are 20,000 units in service totally globally, and it's a big market as well. But it's big motors, it's big rating. I mean, big power, large powers, and very low speeds. So these are huge motors. And you see here, it's an estimate 265 units installed only in the US and 420,000 units globally. This is also a huge market. But again, we talk about a wet cooling tower today and what that cooling tower does. So here's the screen of how the wet cooling tower works. First of all, let's look into this picture here. It's, I believe, self-explaining. We put hot water, processed water. So when you have, let's say you wanna fill up the chocolate cream into the glasses. So you need to heat up the chocolate cream so that it's becoming liquid, and then you have all that heat that you need to cool down again. So here is the hot water that goes in. So hot water runs down the cooling tower, and it's getting colder. I don't want to say it is cold like ice cold. It is just a few degrees cooler when it comes here to that sump, and the customer takes then, or the user takes then the cooled water out. And we reach this by this fan up here, and that fan brings the warm air out. So here is filling material in the cooling tower. The hot water runs back and forth, back and forth, back and forth down, and the fan is pulling the air from the outside, the cold air from the outside, up to the top, middle, and up. And for this fan, we need a motor, and that motor, that is what we are talking about today. So the cooling of circulating water is usually associated with large air conditioning and heat dissipation systems, referred to as large heat exchangers or condensers, depending on the drive configuration. And our direct drive, you will see that very often, the DDCT, the direct drive cooling tower benefits include energy efficiency design versus alternative processes or technologies. Double-digit improvements can be achieved. And this is something I want to touch base on later on as well. Because we are changing the design of the cooling tower a little bit, and that brings great improvements. And double-digit means we can increase the efficiency by 10+%. I had examples of 10.8 as the smallest, up to 24.5%. It's really a big improvement here. We reduce the noise. Like I said, we changed the cooling tower design a little bit. So we take the gearbox out that's usually in there, and that means we have a quiet operation. The motor is in the range of 59 to 62 dBA, and that is reached because there is no cooling fan on the motor, because the motor gets cooled by the fan up here. So it's a very quiet system. The OEMs, by the way, love that. Less need for maintenance. Only motor regreasing is required. So when we take the gearbox out, in the gearbox you need to change oil, you know, every 6 months they say in the instruction manual at least you need to do an oil change. All this is not needed anymore because we are just re-greasing the bearings. It's environmental friendly, no risk for oil contamination. Again, there is the gearbox. You will see pictures of that gearbox later on. And usually we have two weak points on that gearbox: the high-speed input shaft, the sealing on that, where all the oil from the inside stands on that seal, and then you have that fast spinning shaft, and that wears off the seal. So that means that the oil can get out of the gearbox at this place. So that's what we mean by no risk for oil contamination, because our motor doesn't contain any oil. And the critical reliability, suitable for food plants, hospitals, schools, offices, wherever. I mean, wherever we have cooling towers, we have actually installed 4 cooling towers on a museum in Germany. So it's, yeah, wherever cooling towers are installed, you can basically convert this to our system. And less mechanical stress. Usually the motors are turned on direct online. So that means you have a very hard start on the traditional system. But since we are using an ABB ACS 880 drive, which we call here a VSD, a variable speed drive, we start the motor smoothly, and that means we have no mechanical or very limited mechanical stress on that entire cooling tower structure. So it's very smooth and long lasting. Long lasting means safe to use. There's moving components in use. So we have just the motor which drives the fan, nothing else. And that brings me basically to the next picture here, because here you see the traditional system, the thing that we talked about. This is the fan again, and here is the gearbox. And that's what I meant here. This is the fast speed, the high speed input shaft into the gearbox. And that seal might wear, and then you have the oil dripping into the cooling water. So that is what we don't want. But you see here is a coupling, and there's another coupling, there's a shaft in between, and then we have a regular B3 motor on the outside of the tower. So multiple things to explain here. Number one is less material or less components in use. We take that motor out, we take the couplings out, the shaft out, the gearbox out. We just install the motor underneath the fan. So there is really indeed less movements, less components that are moving here. Regarding noise, you see the motor sits on the outside of the tower. So the motor is, the fan of the motor is the noisiest part. So this noise is really on the outside of the tower that you really can hear. Now we have a very quiet motor inside the tower. There is no fan on the motor that makes the noise. The only noise is this fan up here. So it all depends on that fan, how loud that fan is, and probably the water that it's dripping down. The water makes noise as well. But you see here that the noise is reduced a lot by using that direct drive system. To the gearbox, one more thing. We have that high-speed shaft here and the low-speed shaft there. And there's a lubrication issue on that bearing here. So sometimes, or we have seen gearboxes that had separate oil pumps to pump oil up to that bearing. And again, an additional oil pump requires power, requires energy. So this you can save as well if you go to this one. And again, we have just greased, lubricated bearings up and down. So from a technical standpoint, this one here is much easier, much simpler than this traditional system with the gearbox. Yeah, less parts, less maintenance, reduced noise, and improved efficiency. And to see that in real pictures, I brought up these two pictures here. So this is the old gearbox technology. You see here's a gearbox. Here's the input shaft. There's the output shaft, and the fan is on top. And this is what I meant. This is the through shaft here. This is the shaft that is connected to the motor. And you need those kind of guards as well. So what if the coupling dies and breaks, and that shaft here is bouncing up and down and just hits a fan, for example? That whole cooling tower could, when it's fully turning, could be destroyed or will be destroyed if the coupling goes and that shaft hits the fan. That would be a catastrophic failure. And therefore they put these kind of guards in the around the shaft to keep the shaft, at least once the coupling goes, keeps the shaft from jumping up and down. All this again is not needed because we have our motor in the middle, and then we put the fan, you see, directly onto the motor shaft. So the motor is designed for a radial load up here. So the top bearing is our radial bearing that absorbs all the radial load. And the lower bearings, I must say, are keeping the axial load, the weight of the fan. They keep the axial load on the bottom. So from a mechanical standpoint, remember it is a low speed operation. It's a direct drive. So whatever the fan needs to turn, if the fan runs, let's say 50, 80, 100 RPM, this is what the motor shaft turns. So the nominal speed of these motors is in the range of, let's say, 50 to maximum 500 RPM, maximum. Okay, so let's read this here. It's reliable and requires less maintenance, like explained before. No gears in use with no oil, no risk for oil leakages. That is explained here with the high speed. No drive shaft, no couplings needed. This is the drive shaft and the couplings, like I said. There is no motor gearbox alignment. That is also an important factor because you have the gearbox in the middle of the tower, and then you have, I don't know, 5 meters away, 6, 7 meters away, the motor, which needs to be aligned so that the shaft or that the couplings receive less stress. So you need to align this motor gearbox position. Then we have the soft starting with the variable speed drive. Like I said, the traditional units are usually not driving on a VSD, the older versions at least. They have the hard start. We have a higher system efficiency and better process control. Yeah, higher system efficiency. I mean, if you take the gearbox out, you save 5, 8, 10% efficiency that is lost in the gearbox. And better process control, we mean the process control by the VSD. We are not using the VSD just for starting. We are using the VSD for controlling the speed. So remember, if you see a day and you see the temperature in the day, in the morning it starts, let's say, at 10 degrees outside. But over the time till you reach the midday, you might be at 25 degrees. So, and then at night it goes down again, maybe to 10 degrees. So there might be a swing depending on where you are on this planet here. There might be a swing of 10, 15, 20 degrees between night and day temperatures. In the desert, even more. And this is what we mean by better control, because we can now measure the temperature that comes back through the water sump at the bottom of the tower. And if the heat is, or if the temperature is too high, we run the fan faster. Or if at night the temperature is too cool, which we don't need, we can slow down the fan, and we can save energy by this as well, just by regulating the speed of the fan. Lower level of operating noise and vibration. Yeah, we are having less material, like I said, and we have a less vibration on the system, on this entire system. One thing maybe that can be explained here is the fan and the shaft is quite near to each other. So if the fan turns, think about it, there is a freewheeling on 3/4 of the tower, let's say, or even more. And then when the shaft comes here, then it's a kind of a air cushion that is generated between the fan and the shaft. So that means that fan is pushed up actually. It's slightly pushed up when the fan comes over this drive shaft. And that causes vibration, of course. And if you see this one here, it's freewheeling 360 degrees. So there is no shaft going through. That means you have a freewheeling fan and you have no air cushions. So you have no vibration on the fan. It's running much smoother than this one here. So it's quite important, I would say, that vibration is going down. Yeah, and of course the noise. The initial cost might be slightly higher, but the payback time is very short. So what we need to compare, and I think there is many times the customers are not really seeing that, you cannot just simply take the motor, the old motor, and compare it with the new motor. Well, that wouldn't be fair because we replace also the gearbox, the drive shaft, the couplings, the guards, the installation. So what you need to calculate here is you need to calculate the entire system. So take the gearbox price, take the motor price, take the shafts and everything, and then compare that with our motor price. And then the initial cost might not be higher anymore if you calculate everything together that you need, which is I think a fair comparison then. So all in all, you have a lot of advantages. There is hardly any, there's maybe one disadvantage of that system here, that the motor is with its entire weight sitting in the middle of the tower. So if you compare the gearbox weight, only the gearbox weight, and you compare that to the motor weighs more. So the structure that you have here needs to be designed to keep the weight of that motor, which usually is. All the towers are normally calculated with, I believe, a factor 10 service factor or safety factor or so. So it shouldn't be a problem, but that is something that we need to review and consider and remember, that the motor weighs more than the gearbox. And we have a nice installation at Kargil in Turkey. And here we have an old wooden tower. You see that? That's a wooden tower. And you know, when the wood is getting wet over time and tower was quite old, the wood would not really hold the weight of the motor. So the cooling tower manufacturer put a kind of a table or stool or support plate in that tower, which was made out of steel. You see that here, that is the steel frame. That what was put in afterwards to put the motor in place and hold the weight. That is usually needed on wooden tower. But if you talk about concrete towers or steel towers, there is usually enough safety so that the motor can be sitting in the middle. We have here learned, because that was the very first installation, we have learned something here. One thing is that solid plate. That shouldn't be a solid plate. It should not, because the fan is pulling the air out of the cooling tower, and the motor is designed with its cooling fins that the air streams by the motor and picks up the heat from the motor and brings it up. Now, if you place a plate like this underneath the motor, you block the airflow. That is not a good design here. And I brought that picture up on purpose because I just want to show you there are some mistakes that you can do if you think, we do it right, we put a nice big solid plate there for that motor. That is not really a good thing. because the motor sits in the shadow of that plate and gets no airflow and no cooling air. So remember this when you see a cooling tower made out of wood, and think about or remember that picture here. And if you put an open grill in here where the motor sits on, which is as strong as this plate, and it's fine. Then the air can flow through this grill and then along the motor side and pick up the heat. Okay. This is the motor. One more picture of the motor. It's a thin laminated frame. So it's a kind of a servo motor design. The frame is the stator. The stator metal is this housing. So it's a very efficient cooling system, because you are not sticking the stator of the motor in a kind of a frame, and you have a heat transfer between the stator frame and between the stator metal and the frame metal. So it's very efficient cooling here, which gives you a very power dense motor. In addition, it is a permanent magnet motor. So we have a permanent magnet rotor inside the motor, which results in no rotor losses except the bearing friction losses, but no other rotor losses are there. So that means that the motor is very, very efficient, and enables the motor to be compact enough for direct drive cooling tower. And here the thin lamination frame in the fan air stream provides optimum construction for the application. Only if you don't put a plate underneath, you know, and you have an open one, open structure, then it's fine. Yeah. This is an example here from an installation in Germany again. What we have done here is to increase the airflow over the motor, because we are a little bit depending on the fan, how much air goes by the motor. And this is something that we can review individually. There are some pipes in the structure here, the pipes for increased direct drive cooling tower motor cooling. And I like to explain that a little bit. So here you see the fan hood, of course, you see the fan, the blue is the motor, this is the cooling tower structure. So it's all about these pipes that we put in here. Remember, if the fan turns, the fan sucks the air out of the cooling tower. So that means that there is an under pressure somewhere here around the motor, or even lower, because the fan is turning and brings the air out. So what if you just put a pipe there, say a regular wastewater pipe from your Home Depot, Bauhaus, from your market where you buy your stuff for your home, not the furniture though, but the tools and so on. So if that pipe is in there, you open up actually a small hole from the outside to the inside. And due to that under pressure here in this area, air will stream from the outside to the inside. And now you will funnel the air right to the motor. So now you can use a plate like shown here, because you bring the cooling air through those pipes. And you bring them nicely around the motor, four pipes, maybe 8 pipes, 6 pipes, whatever you want. We can then measure the airflow over the motor, and we can make sure that the motor will not overheat. So this is actually a good method. It's an inexpensive method, because those pipes are very inexpensive to reduce basically the motor size. And remember, the price of the motor is depending on the motor size, of course. And if you bring more air over the motor, you can live with a smaller motor, and a smaller motor costs less. So therefore, we are saying here a cost-efficient solution to keep the motor cool, resulting in a smaller motor and less initial cost. So a smaller motor that might cost less, or a smaller motor will cost less. Okay. Then we compare just one more time the induction motor. Hey, this is a standard induction motor out there since I don't know how many hundreds of years. It's a stator rotor. By the way, yeah, sorry, common. What is common between an induction motor and a permanent magnet motor? The stator, the rotor diameter is the same, and the three-phase power, of course. This is all the same. So on the outside, everything is the same. And you see already the difference here is the north and the south. So that means this is an induction rotor here, and this is the permanent magnet rotor here. So the difference is it can be line started. Yes, it can, but something we don't want to do on a cooling tower because of the mechanical stress. Remember this. And that motor has slip. So we don't really know what the speed of the fan might be. We have losses in the gearbox. We have slip in the motor. We can only estimate what the speed of that fan will be. Well, here the difference is the motor, the permanent magnet motor, requires a drive or similar to start. But this drive helps us to reduce the or improve the efficiency even more, reduce the losses, because now you can speed the fan, you can drive the fan to its optimal speed depending on the temperature. Remember the example with the temperatures at day and at night. Now you can really run the fan at its needed speed. It is synchronous, so we know exactly what the fan speed is. And the rotor has no losses. Like I said, permanent magnet, except the friction of the bearings. That's the only loss we have there. This is how we put the magnets in the rotor. So it's a little bit an explanation of how our bearings look like. Sorry, not bearings, rotors look like. The magnets are actually inserted into the rotor, and I can only highly recommend to use our motor or this cooling tower motor with our ACS 880. This way you are sure that we know where the magnets are, in which position the magnets are. You see here the magnetic lines. So we know exactly what we have built in the motor. We have transferred that knowledge over to the drive, and the firmware of the drive is especially for these rotors here. So please do not even think about using a different brand drive on these cooling tower motors. We have had that in the past, and we had some failures, stator failures, because of other drive brands that were not capable of running our motor. And this technology, like I said, it's a proven technology, is coming out of these servo similar motors. We have these square frame motors, usually used for winders, let's say, high speeds, high constant horsepower speeds. These motor designs are used in, like I said, in the steel and the paper industry, where you wind paper up and steel up and down. So this is a very reliable motor design out there since I think since the early 80s. So it's 40 years on the market, that design. Here you see a rotor which has the magnet slots open, and there are the magnets inserted. But you must not think that the magnets are kind of bars. These are just little, say, 3 times 3 centimeters chips that we stick in, because what we need to achieve is we need to skew the rotor. That means if you have the shaft, the key of the shaft here, and you jump with the magnet in here on this side, then the output, so the other side of the shaft, the other side of the rotor, the magnet doesn't come out at the same position. It is a little bit twisted, a little bit skewed. This way, we are reducing the magnetic vibration inside the motor. So we skew the rotor, and that is the reason for these little chips of magnets that we put in here, just as an explanation. So the rotors are skewed. That's the main message. Then we have a size comparison. This is me. I'm 1.80 meters tall. So that motor is maybe 1.60 meters. That's the largest one we produce. That's the FL58 size motor. So we have basically 7 different sizes in production, and this one is the biggest. That weights like, I don't know, 3 BMW 7 Series or so. That is quite heavy, that motor. Okay. Now we have some customers that are saying, yeah, well, but you know, we stick an electric motor in a very wet environment. Is that motor really suitable for doing so? Do we really want to put that electrical piece inside the cooling tower? And I must say yes, because we are using a sealed insulation system, and that sealed insulation system is tested underwater. So this is a water pool, let's say, where we put the winding in, and then we energize it and see if there's any leakage, electrical leakage. And we're using this data for the top drive industry as well. So the drilling, the offshore drilling application. Here is a motor, our motor actually, and that motor is open, that drills this pipe down in the ground. And you can imagine in the North Sea, where you have all the salts and the humidity and chemicals and whatever, this is really an open motor, and the air just goes through the motor. On the cooling tower, we are using a totally enclosed design, and we are sealing it up here. We are sealing it quite well because we don't want the water running through the bearing into the motor, because then we are washing out the grease of the bearing, and then we have a bearing failure. So therefore, we are using a very good seal, premium seal on the one end only, because we have only one shaft. Remember, a gearbox has 2 shafts. This is the seal. This is the seal that is the standard seal, the original one. That is the one we've used in the past because we had nothing else designed for us. That was a standard seal. And now we have improved that. We have a different angle here. So you must turn that, you must think about, or you need to turn your head like this so that you see the top side. This is the top side of the seal. It's a much wider seal now. It's a very small one, and it was flat. Now it's a little bit tapered so that the water can run to the outside. It drips off. We have a grounding brush, a shaft grounding brush included now in the seal. So all the motors will have a shaft grounding. There you see it. This is how it is installed afterwards. So when we talk about the seal rotor, then it's the OD seal rotor. That's the outer side of this. So this rotates. Therefore, it's the rotor, not the rotor of the motor. So yeah, I think we can read that here. Increased seal rotor outer diameter, added taper to the seal rotor, like I explained. Increased internal allowable movement for excessive vibration. So if, for example, you have an unbalanced fan or a dirty fan, so the fan is getting dirty over time, it starts vibrate more. So that doesn't hurt the seal here. Increase the number of O-rings on the seal from 1 to 3, 2 of which are conductive. So because of the shaft grounding, we are bringing the shaft current down here to the motor frame. And we have 2 solid carbon brushes added to this seal. So one on this side and one on the other side, which we haven't had before. So that's an improvement over the years. This is what we produce. We have power from, it's just just a number, because very often I get just the question, what power range is that motor in? Well, you can't really say that because it depends on the speed. It really much depends on the speed. So we have the powers from, let's say, 7.5 kW all the way up to 186 kW, depending on your speed. And these are the frame sizes that we are producing. These are the IEC equivalents for these. So a FL32 is actually an IEC. There is not an IEC or NEMA standard on cooling towers because we are replacing a gearbox. So there is no standard for that motor per se. And then we come to our success story here. The cooling tower was built in Clemson University. That was built in 1986. There is the details. We had the motor on the outside, traditional system. We had the gearbox inside, and we had a fan. And I want to run through that real quick because the fan load hasn't changed. We used the same fan before and after. Before the conversion was the same fan installed as after. We took the gearbox out, which was a 90.2% efficiency. We don't need that anymore. Means the horsepower that we sticked into the motor was already 46 at that point. Well, here on the direct drive, it's 41.5. Motor efficiency used to be 90%. We had a 93.1 on that motor. We haven't had a drive, but now we need a drive which is 1.2% efficient or losses. And that brings the input power from 51 down to 45.1, which is a 6 horsepower saving, or put it in percentage, it's 81 to 92. So it's an improvement about 10.8%. And now somebody can argue and say, well, a gearbox doesn't have a 90.2% efficiency. Well, not on the data sheet. But if you read this here, the gearbox manufacturer said it's 96% efficient. But in reality, the whole system with couplings and drive shaft was only 90.2. And it was measured, really measured. So energy efficiency compared to Denmark, like I said in the beginning, in Denmark, we had 10.8% savings. Remember that number. It is the same like before. You see here, it's a 10.8% saving in the US, and it's a 10.8% saving in Denmark. So it is really not a measurement mistake. It is really indeed we can achieve a double-digit saving. And if you see that, the efficiency actually, the percentage is increasing the slower you run the motor. That is the beauty of this permanent magnet motor. It keeps its efficiency much longer than an induction motor. So at lower speeds, you're even saving more because the efficiency of the motor keeps up. That is the noise. We had the induction motor tested with a microphone on the outside of the tower. So we measured the birds singing and everything. And then we have, after that conversion, we have measured the same again, and we come down to 5 dBA, which is a lot. And like I said, our motors are just in the range between 59 and 62 dBA. So the highest noise level reduction I heard was from Austria, reported from Austria. It was 12 dBA. So maybe something was wrong with the tower before. I don't know, but 5 dBA is definitely achievable. Our key findings, the laminated frame interior permanent magnet motor technology enables direct drive gearless system. We have the low speed lubrication eliminated. We have the high speed gearbox sealing issue eliminated. We have no drive shaft, no coupling, no guards, no alignment, nothing. The motor can be configured to be a replacement. So the shaft diameter, the shaft length, the height of the motor, all can be designed for the replacement of the gearbox, the existing gearbox, if you want to do a revamp or an upgrade. The system is vastly simplified, of course. Significant improvements were achieved in overall system efficiency, of course. the biggest improvement was definitely taking out the gearbox. And the ABB ACS 880 and the plus code N5350 is needed to run the motor. But this drive is giving you so many advantages, like the smooth start, like the speed control. There are other features in like the trickle current heating if the motor is at standstill. So it gives you a lot of benefits. The direct drive motor solution reduces the noise of the motor, of course. So I need to speed up a little bit. Links and sites. We have multiple websites and a selection program. That selection program can be downloaded from the internet, and then you can select by entering your kW, your speed, your voltage. You can calculate your own motor, and it gives you electrical data and mechanical data as well. I can only highly recommend this, to download this program. It's a really good one. Yeah, as a summary, energy efficiency, double-digit improvement. Remember that statement is achievable. Noise is a reduction, very quiet motor operation without the gearbox. Maintenance reduction, we have only the motor regreasing, not oil changes every 6 months. Environmental friendly, we have no oil contamination of the cooling water. It's reliable. Well-proven motor design in use, less mechanical stress because of the smooth start, and it's safe to use, less moving components. So next steps, how to approach an installation. Well, you need to quantify your annual maintenance cost of the traditional cooling tower motor gearbox design per cooling tower. If you have that quantified, if you know what the maintenance cost, let's say they say, well, maintenance of that cooling tower cost me $5,000. Well, then this is a number. That's what we quantify. Then we need to evaluate the option to modernize the traditional cooling tower design with the cooling tower direct drive solution. So that needs to be reviewed. Most likely it is possible. Then quantify the potential savings with the cooling tower direct drive, and proceed with the retrofit of unit 1 on phase 1. So what we are saying is, if you have the potential savings with the energy calculation, with the of course with the reduced maintenance, but also with the installation of the new one, just try it on one unit. Don't think that you have a cooling tower which has five towers in a row, like in Cargill, and you need to convert them all. We didn't do that either. We had one tower, one fan converted, and had 4 others running normal. Cargill was so impressed by the performance of that one tower that they have changed the other 4s just immediately thereafter. But they needed to be convinced. So don't think that you need to sell all 5 at the same time. That's a lot of money, and that's, I think, not really needed. Just try one and then see how it works. You will be impressed. And then document the improvements and move forward with phase 2 and upgrade all the other inefficient motors with the direct drive. This is the way to go forward. And with this, I say thank you, and I hope that we have received in the meantime a couple of questions. Britt,
Yeah.
hope you're still there.
Yes, I am still here. Can you hear me?
Yes. Very
Okay,
well.
perfect. Yeah. Thank you so much for the presentation, Michael. And yes, please, everyone, if you haven't already put your questions into either the chat window or the Q&A window, now it's time to do so. So hopefully we will have some more questions, but I have already received a couple of questions. So let me start with the ones we have, Michael. Mm-hmm. So here is the first question. What is actually the, let's say, average energy reductions that you have achieved for this solution?
Well, like I said, the 10.8% is just achieved on full speed. So that means that if you compare a tower with and without the direct drive, you can achieve a double-digit improvement. So 10% is achievable by just removing the gearbox. If you now operate the motor or operate the fan on a drive, which you haven't done before, then you can save even more. Because you must imagine, if you have a cooling tower, just one cell, just one fan, that provides you on or off 100% cooling or no cooling, you are wasting so much energy. What if you need 20% cooling? You need to turn it on, you need to have 100% cooling, and you're paying for that 100%. While when you drive this on a VSD, then you can run the fan to a lower speed and operate that at 20% where it needs to be. And then you have additional savings. So 10% efficiency by the gearbox plus whatever you have on the drive.
Okay, thank you very much. And the second question I would put forward to you is that what is the warranty time you are promising?
Well, the warranty time for these motors is 5 years. 5 years or 60 months. And we have an additional 6 months shelf lifetime. So all in all, if you talk about a standard stock product, then we are talking about 66 months, which is 5.5 years. If you have a produced motor, a motor that is custom made for your application, then it is 60 months, which is 5 years.
Thank you. The third question coming up here is because this is sitting on the roof and the weather conditions might be very different. Does it fulfill IP66?
Oh yes, absolutely. It got a stainless steel conning box on top of that, and yeah, it is definitely an IP66, and it's quite easy to achieve. You remember the installation of that motor, or the design of that motor. It's a totally enclosed motor. There is only one shaft end coming out, and that's what we are protecting with this Infro Seal, that upgraded Infro Seal. So yes, it is an IP66 enclosure. Yes.
Okay, thanks. Next question. What is the considered maintenance?
Say that again. You are breaking up a little bit.
Okay, so I try again. What is the maintenance interval?
Oh, how often you need to re-grease the bearings? That is basically, yeah, well, we are saying every 2 years is the re-greasing period, but 2 years is the operational time, which is even longer. But I don't want to discuss that, because what we are saying is the motor should be inspected once a year. And it is not only to re-grease the bearings, but it is to check if the drain plugs are open and clear. Because if the drain plugs are plugging up, then the water that might be inside the motor can't get out. And then you fill up the motor with water, and then the lower part bearing will be hurt. So let's say it this way, once a year a check.
Okay, thank you very much. I think that is what I have for now. And
I wanna maybe, to the last question, I just want to say or something add to this, because a cooling tower is usually not maintained but cleaned once a year anyway. So remember with the bacteria, with the Legionella, we call it.
Yeah.
We need to clean, or the user needs to clean the cooling tower, and that's usually once a year. So therefore, while they are cleaning the tower, they should just simply check the drain plugs if they are okay, and maybe re-grease the bearings.
Yeah, right. And of course, also look at the VSD if there's anything on that side as well. Right? Okay. I think if there are no further questions, no, I can't see any more questions in the chat and Q&A window. So hopefully then, good to have you all in this webinar. Thank you very much for attending. Thank you so much, Michelle, for this very good presentation. And if there is any questions, you can also, of course, contact us afterwards. And we will share the recording, we will share the presentation on our webpage. And we, of course, welcome further interaction on this. Thank you, everyone, and have a very, very good day. All the best. Thank you so much.